so we might want to continue in the talk. So let me briefly introduce the idea of what Ludovica is going to present. Ludovica is she is beginning her second year of her PhD here in Bordeaux. She was previously in Milan with Simona Perotto. So going in the direction of the two problems that Florian raised. One, it's the scarcity of the patients, and the other, so it's not that the patients are few, it's that the patients we can track are few, okay? So this is one problem, and second problem is to get risk factors within minutes, and possibly with robots that are running on the PACS of the hospital, so in the data of the hospital. One important issue is to have a geometrical model of the aneurysms, and Ludovica is attacking this problem to have a geometrical model of the aneurysm and to generate new shapes to contribute to the problem of the scarcity of data. Please, Ludovica.
Okay, good afternoon to everybody. I'll share my screen. Can you all see?
Yes.
Yes. Everything all right? Okay, great. Thank you. So first of all, thank you for the introduction. This afternoon, I will talk to you about a parametrization and generation method for the abdominal aortic aneurysm. This work has been done in collaboration with Florian Nurea, which I thank, and also with Professor Morbiducci in Politecnico di Torino and his team members, Valentina and Carol, which I thank very much as well. So first of all, I will introduce very briefly the problem of the abdominal aortic aneurysm, and then I will detail the pipeline to generate new aneurysm shapes that articulates mainly in 3 steps: parametrization, a reduction phase, a sampling phase, and then finally I will present the result I have obtained so far. Well, Florian has already talked about what an abdominal aneurysm is. Normally the diameter of the aorta in the trait between the renal arteries and the iliac is 3 centimeters. And when we have an aneurysm, this diameter grows. And the progression of this disease is that an enlargement of the aneurysm until it ruptures. The rupture is a life-threatening situation, and so once the aneurysm is detected, of course, surgery is taken into consideration. But also clinicians have to decide whether operate or wait for, or maybe wait, because also the operation has some mortality risk, of course. In any case, the current criterion for surgery is as Florian has already said, is the maximum diameter. When the diameter exceeds 5 centimeters, then surgery is taken into consideration. However, this criterion fails when in the case of the so-called false negative and false positive, namely some aneurysm with a diameter that is below this threshold to rupture, and some aneurysm instead remain stable, even if their diameter is much bigger than 5 centimeters. Here in the right, I am just listing a few of the other rupture risk factors that have been proposed in literature. These ones take into account, for instance, the already mentioned wall shear stress or the strength of the wall, are related to the fluid mechanics. But in literature, you can find maybe others that depend on the geometry of the aneurysm, for instance. In any case, the problem is that we need to find a reliable rupture risk factors that a clinician can use. However, these rupture risk factors must be tested somehow. And there is the problem, the difficulty of collecting data and the scarcity of large data sets so that the factors can be properly tested. And here comes into play the generation of new aneurysm shapes. So the general idea is to perform then some data augmentation on a small data set available to us and to construct a generation algorithm. The strategy we have elaborated can be seen as a variational autoencoder. So we start from an initial dataset X, which will be provided by Inria, and then we perform some reduction processes, and we find the so-called latent variable Z. We can see the latent variables as a compressed representation of the initial dataset X. Then we exploit the normal distribution to model these latent variables, and we sample from this model, obtaining the variable Z tilde, and then we reverse the reduction process we have just done, and then we obtain a new data, which is X tilde, that was not present in the initial dataset. Now, of course, variational autoencoder are based upon neural network. I am not using strictly neural network. In the so-called encoding phase, I am instead using first the parametrization phase, and then I am exploiting proper orthogonal decomposition, and then the decoding phase is then simply the reassembling of the aneurysm shape. So let us start with the initial dataset that is provided by Inria, which employs a software called Aortic. Here on the right, I am just showing you a few examples of the aneurysm I am working with, so where my pipeline does start. And it starts with the parametrization. So Aortic gives us the skeleton and the 3D geometry of the aneurysm. The first thing we do, we take the skeleton, we exploit an algorithm that uses the distance function, and we center the skeleton in the geometry. Then we parameterize the skeleton with the B-spline with the S points P. And this vector of S points is what we call the center line. Now we want to parameterize the aortic wall. For every point of the center line, we compute the frame tangent normal by normal, and then we cut the 3D geometry on the normal by normal plane. What we obtain is shown on the figure on the right. We obtain the points of the intersection in between this plane and the 3D geometry, and these are the points in orange. This is what we call the section related to the point PS of the center line. A small technical detail at this point, the frame tangent normal by normal we are using is not the frame because the center lines sometimes have some straight traits, and on those parts the curvature is null. And using the frame was giving us some problem in that reassembling phase, the decoding phase, so to speak. And so we have turned to a more robust technique, the minimal rotation frame, which is another standard technique to build a tangent, normal, and binormal vector. Okay, now we have our points, and we see, let us look at the figure on the left. The thing we do now is we compute the distance in between the point of the center line and each point of the section, the distance r, with respect to an angle theta, starting from the normal vector. So we obtain the couples theta r that describe the profile of the section, and this profile is then approximated with a Fourier series of degree nf. In the figure on the right, in particular, you see the initial profile in blue and in red, the Fourier approximation. We do this for all the section, and this is how the aneurysm parametrized looks like. So in the figure on the right, we can see in red the center line P made of S points. And for each point, there is a section in white that is parametrized with the Fourier series of order NF. If we now collect for all the section the coefficients of the Fourier series in the vectors A0, AJ, we can then identify each aneurysm simply by its center line and the Fourier coefficients, the vectors of the Fourier coefficients. Very well. Now we ask ourselves, how many degrees of freedom, how many variables are we employing so far to describe the aneurysm? Both the center lines and the vectors of the Fourier coefficients live in the space Rs. Since for us, S is 100, S is the number of sections, and then we made a computation, and the number of degrees of freedom we are employing is 10 to the power 3, which is too much. What we would like to do is to lower this number, namely to find the function f depending on z, where z are the latent variables, and live in a space Rn, where n is much, much lower than this 10 to the power 3. And we employ the proper orthogonal decomposition that allows us to make an approximation. For instance, we can then approximate the center line P with a linear combination of NP basis function phi based on the dataset we have, multiplied by some coefficient C. In this case, our latent variables are going to be the coefficients of the linear combination that live in the space RMP. Therefore, our goal with the POD is now to approximate each one of our parameters with the lowest number of modes possible. And so we start. First, we have a look at the center line. And here you say how the POD is performed. Well, on the on the left, first of all, we see the center line scattered on the 3D space. This is because we have, when first the data are collected, this is how the center line are disposed. We want to minimize this artificial scattering, and we use the so-called, what is called the generalized procrustes analysis, which applies the rototranslation, a reflection, and the scaling to the initial center lines, so that they look like the figure in the middle, and they are all they have all the same length right now. But we have kept the original length, and we consider it as a latent variable. Then we apply the POD to this pre-process set of center lines, and what we have is the POD approximation. In the figure on the right, you see in red the original center line, and in white a progressive approximation as we increase the number of POD modes. And so we now collect all our latent variables. We have, once again, the initial length of the center line and the coefficients of the POD linear combination. We do the very same thing for all the Fourier coefficients. Here I am just showing you the mean radius. Once again, on the left, the first disposition of the mean radii. Also here, we apply a pre-processing. We do not use the procrustes analysis. We just translate all the radii so that their average is 0. This, the translation, we keep this value, we will call it offset, and this will be another latent variable. Once again, we apply the POD, and we have the coefficients of the POD linear combination. Very well, right now we have applied the POD to all our parameters, and then we can collect all the POD coefficients of offset and initial length and build the vector Z of the latent variables. We can also compute the dimension of the space of these latent variables, n star, which is going to be the sum of all the dimensions of the POD reduced space, plus some extra dimension, one for the length of the center line and one for each of the offsets. Okay, how much is n star? That is, how many latent variables are we using with the POD approximation? To do so, we would like to compare the initial shape of the aneurysm, so the original one, and the one reconstructed with the POD approximated parameter. Okay, to do so, we define the following error. Let us take an aneurysm K of our dataset. We apply the POD pod to the parameters, and then we reconstruct this very same aneurysm with the approximated parameters. Then let us take a section of the two aneurysms. Let us perform the relative error epsilon s. Here we are using the L2 norm. And then let us compute the average over all the sections of the aneurysm, obtaining for the aneurysm K the error epsilon K. The epsilon K quantifies the projection error of the original aneurysm through in the POD reduced space. We have found so far that if we are happy with an average error over all the dataset of 10 to the power minus 2, n star is of order 10, which is not bad. And so now we are ready to operate in our space of latent variables and to work with the normal distribution to extract new latent variables. To do so, I am just going very quickly to introduce a tool that comes from machine learning, which is the Gaussian mixture model. The Gaussian mixture model is a technique based on the maximum likelihood principle, and what it does, it takes a certain number of Gaussian distributions and models these Gaussians to model the distribution of a certain input data. You have an example in the figure on the right. You first see the contours of, on the small figure on the left, the contours of the three Gaussians employed, and on the left, the overall distribution over a certain dataset. How are we going to employ the Gaussian mixture model GMM? Well, we are going to apply this construction over our latent variable Z in Rn star, and then we are going to sample from this distribution so that we obtain Z tilde, and then using the new latent variable, we are going to rebuild a new aneurysm. However, we must face a few challenges. The first one is that n star is still too big. The second one is that we cannot use many Gaussians because we have very few data. And so we have elaborated the following strategy. Okay, the strategy articulates in 5 main steps. First of all, we break the vector Z of the latent variable in n subgroups. And this is done in the spirit of getting an even lower dimension for the latent space. In this case, we are proposing, for instance, to consider the center line alone and then to split the Fourier coefficients into groups. Then, for each group, we set a certain precision in certain projection precision for the POD. In this case, for instance, for the center line, we require a precision of 99.9. We are able to attain this eta with 4 POD modes, and therefore the space where we will build our Gaussian mixture model will be a space of dimension 5, the 4 POD modes plus 1 extra dimension for the length. Then step 3, we'll build our GMM. We sample from it. You see it at the bottom line, the figure on the left. There are the black dots are the initial data. You see a projection into dimension of the GMM. In black, once again, there are the initial data, and the purple star is the sample coefficient Z tilde. And then we use the sampled tilde variables to build a new centerline in this case. Okay, you see now in the figure on the right that the new centerline is in red and all the others are, the initial ones are in white. This new centerline we have created is statistically relevant by construction because we have extracted the parameters to build it from a Gaussian distribution. We do the very same thing for the other two groups, for the Fourier coefficients, and we end up with the Fourier profiles that are shown in the figure on the right at the bottom. Okay, now we have a center line, we have some Fourier profiles, and we can rebuild, we can build an aneurysm, a new shape that was not present in the initial dataset. One small thing, we have proposed in this example subdivision in groups and a certain projection precision threshold, but we have seen that we can play both with these two parameters, let us say. Namely, there are many combination of subgroups, or we can increase or decrease the threshold, the precision that we require, and we have seen that we get similar results, more or less. And here is another, there are other examples, reality versus generation. Okay, on the left, of course, the aneurysm provided by Nurea, where we started from. And on the right, some aneurysms that I have generating with this pipeline. And okay, so here is where we stand. We have a generation technique that permits us to create new data starting from an even small data set, the data that are statistically relevant once again and realistic with respect to where we started from. And in perspective, this work, how can it be used? Well, of course, it will be used, for instance, by Valentina and Carol. Now I'm maybe anticipating, but anyway, to make more fluid dynamics simulations so that we are able to test better any risk factor that we might come up with. And so I am thanking very much all of you for your attention, and I am available for any question.
Thanks a lot, Ludovica. Very good. The discussion is open. Please, if there are questions.
I have a question. Congratulations, Ludovica. Very nice presentation. I have two questions indeed. The first one is and if you are able with your approach, actor models,
I am afraid there are some connections problem.
Umberto, there is a problem with the connection. We didn't hear you.
Oh, sorry.
Okay, so Umberto will try to reconnect. In the meantime, if there are any other questions or issues that you would like to discuss,
yes, Angelo, this is Thomas.
Please.
Thank you very much for this very nice talk, Ludovica. Well, I have a question which is absolutely, if you want, heuristic, is that I would like to know whether the more singular flow within these arteries, these deformed arteries, could take place in the regions where there are corners, okay? Because you know, when we do the POD analysis, it tends to smooth the boundary, okay? So the point is that if the flow, normally we know that the flow are rather singular near corners, okay? Mm-hmm. So perhaps it is particularly important to model the aneurysm in such a way that the corners are kept. So the question is whether really the true blood flow is more singular whenever there are corners, okay? And what then it would be important to model those corners. Okay, yeah. But this is absolutely heuristic. I have no idea, of course.
No, it's thank you very much for your question. It's a good question. Indeed, so far I haven't thought of the importance of modeling corners, but this is just because in general the geometries I was starting with to work with were quite smooth. So this is the first thing. But for sure, if we want to be able to capture more detail, let's say, in the mesh, what we have to do would be to increase these figures, these numbers here, because by doing so, we will increase the number of POD modes that we will use. And this will ensure us to be able to reproduce more all these details that we are capturing. However, this has also a drawback, because if we take a high projection precision, it means that the POD space that we are using gets bigger. And building a Gaussian or many Gaussians in a high dimensional space makes the whole the model not really meaningful. We risk to have too many dimensions, and so we might get some results that are not even physical. Like I have seen that trying to increase this number to get more precise shapes at the end was also creating some very unphysical, because then there is the problem that all these parameters are all correlated. And when we are splitting in subgroups, we are assuming, okay, there is correlation within this group, but not among the groups. So it is, yes, if we had more data, for sure, it would be easier to, let's say, have maybe more, to be able to reproduce these angles or all these maybe bumps or strange shapes that are typical of aneurysm. Another thing would be to, in the parametrization part, maybe also can be done to increase maybe the number of sections we are using. However, we have seen that since the trait is more or less 10 centimeters, if we take 100 section, it means a section each millimeter. And if we take too many sections, the risk is to create some data that are not maybe there, or maybe increase the number of the points we are considering on the center line. I have considered, I think, 160. So, and even there we have checked that, yes, it's 1 point every 1 or 2 millimeter, more or less. But yeah, so this is, I hope these figures help having a better view of this problem.
Okay, so thank you very much. This is something to be really thought a little bit. Thanks.
Sure, thank you.
Thanks. Umberto, you want to pose your question?
Yes, can you hear me now?
Sure.
Yes.
Okay, good. Very quickly, my first question is, can you extend your approach to include in the model representation also the iliac bifurcation?
So far, no.
Or is it feasible, maybe in the future?
I think it will be something feasible, because yes, because there would be the question of splitting the center line.
Okay, my second very quick question is, have you are you planning to use the coefficient of your POD representation of the aneurysmal sac in the future to explore if there is they have some prediction strength, maybe to predict the evolution of the aneurysm?
Well, yes, like once we are okay, yes, well, this method can be also used if we wanted to, if we are able to map on the surface a certain maybe CFD solution, and then if we want to compare what this like what this solution means for two different aneurysms, the idea would be to map the geometry, because different geometry, different solution is starting to get complicated, like to map these two solutions onto a cylinder so that we are working on the same geometry, and then to perform the cylinder, the POD on the two cylinder. So in this sense, like this is further work, of course, but in this sense, there is the possibility, of course, to exploiting this very same method to obtain some POD coefficients that are meaningful to make comparisons and predictions also in time.
Thank you very much.
Thank you.
Thanks. To go in the direction of what Ludovica was saying, the idea would be indeed, Umberto, to use those coefficients and to correlate them to a risk factor that would be computed by, for example, one of the risk factors that you propose with your team. Once we have this correlation, we could, from those coefficients, extract directly the risk factor. That would be the final goal, let's say.
Okay, thank you.
Thank you. Thank you. So thanks, Ludovica. Very nice.